Hello, I'm Eddie Hill from ZEISS, and today I'm going to be telling you about Mineralogic. This is a general overview of the feature. So we'll have a brief introduction. I'll then move on to speaking about how we classify items in Mineralogic, the results and outputs that we provide. I'll spend some time talking about the flexibility of the software, of the method, and this is really expressed and evident in the data acquisition methods. I'll talk about some of the latest developments in Mineralogic and provide you with a summary at the end. Just bring everything together for you. So what is Mineralogic? Mineralogic is an application that sits on top of the SEM and performs image analysis or controls image analysis, image processing, EDS analysis, and the SEM itself all together to provide a material analysis with a high degree of flexibility and high precision. We then, at the end of the analysis, immediately provide the data outputs. It's platform independent. This means that we can install it on a fed column SEM, a tungsten, lanthanum hexaborate, or our remote ruggedized unit, the MinScan. It's modular and recipe based, which adds to the flexibility. This means that once you have prepared a method for image analysis or image processing or a set of tabulated outputs, you never need reorganize these again. You can call them from analysis to analysis in what we call a recipe. We create a recipe that describes the analysis and operates the system automatically for this analysis. This provides flexibility and ease of use. So one operator can create many recipes that can then be used by other less trained or skillful operators. We focus on data quality and accuracy. It's very important to us. And for this reason, we use quantitative EDS rather than, say, spectral matching for the classifications. It contains a full image processing library, and we can use any input image from any of the detectors on the microscope, be it the backscatter electron detector, cathodoluminescent secondary electron detector, or any other detector you may have mounted. And of course, we provide a system for offline data manipulation and processing. You don't have to do everything at the microscope during the analysis itself. At the end of the analysis, we provide many outputs. Some of them are mining specific. Amongst these would be bulk mineralogy, assay, distribution, liberation, association, free surface liberation. But we'll cover these in more detail further on. As we said, Mineralogic operates on an SEM, and it's a fairly simple system where we use the high resolution image that the SEM provides. We use EDS, spectrum specifically, and quantify this to be able to classify the elements and then classify the mineralogy of the sample. All of it runs through one single PC, and immediately at the end of the analysis, we have the results available. So having said that, we use automated analysis and we quantify DDS spectra. How do we classify? What are these results that we provide and the outputs? We have several mineral classification options. These can be used individually or in conjunction, which again adds to the flexibility. Use quantitative EDS. So the classification is independent of the system being used, and it's solely based on the stoichiometry of the material being analyzed. In this case, we have, as an example, chalcopyrite, where the composition might be 35 weight% copper, 30 weight% iron, and 35 weight% sulfur. And it's this weight% distribution of the elements that we use within the mineral library in this case, or could be the materials library. Since we have the weight proportion of the elements, we can also use element ratios in order to better classify. So the element ratio can be used in conjunction with the chemical stoichiometric description itself to further refine or split the analysis and classification. Now, independently or as adding further criteria to the classification, we can use the backscatter detector. We use the grayscale of the material as a response to the backscatter detector. And we have an ultra high contrast backscatter detector that enables discrimination of minerals with a delta AMU of approximately 0.07. And more recently, we have added morphology. So the mineral shape characteristics or the grain shape characteristics can be included in the classification for ultimate mineral discrimination. And here we have an example of how morphology aids in this classification during the analysis. Again, this happens automatically in line with the analysis. So on the left-hand side, we have a backscattered electron image. And immediately you can see that we have some brighter grains or particles and some darker grains or particles. The reality of the situation is that both of these are goethite. The bright ones are vitreous goethite, and what appear to be darker ones are ochreous goethite. We see them as darker because as humans we have already processed this image and we've taken into account the black of the porosity that these exhibit, that the ochreous goethite exhibit. And so we can distinguish between these two features. To a backscatter electron detector, for example, which sees every pixel, every bright pixel of the image, then the gray level of both is the same. So we couldn't use gray level to discriminate them. The chemical composition of both is the same. It's the same mineral after all. So, but the difference between them is the porosity. So Mineralogic uses that measurement of porosity during the analysis to differentiate between the vitreous goethite and the ochreous goethite, as you can see on the right-hand image where these have now been classified. So why quantify the spectrum? We have a standard spectrum, counts on the y-axis, and a KV or energy along the x-axis. We have that this spectrum could correspond to 27 different minerals. Now, if we have the weight percent distribution of the elements present, we can immediately start to narrow down what minerals those would be. There's much less error in this method. So this spectrum could be split, could either be chamosite or Klein or Claw. Using the element ratio rule, we can soon differentiate and decide that this is chamosite. So we can identify the mineralogy with high confidence by using full quantification. And here would be the corresponding spectra for both of these minerals. And admittedly, we can see that in the Klein or Claw, we have a higher magnesium peak or slightly higher silicon peak and a lower iron peak. But the peak height alone cannot give us the level of concentration of an element in a system. And here we have an example with illite and orthoclase, where again, the differentiation is simply the concentration of some elements. If we're using the spectrum alone, we are not correcting for matrix effects. So in the example I have here, the iron peak has a high absorption in a chrome-rich phase and low absorption in the presence of manganese. Unless we convolve the spectra to quantify the elemental presence using accepted methods, we can't really determine which of the phases the spectra corresponds to, because the peak height is not indicative in itself of the concentration of that element. So the intensity of an X-ray peak depends on other elements present in the analyzed region, and these we call matrix effects. Analysis with energy or with standard calibration is something that we have been discussing internally for some time, and we now provide with Mineralogic. So what do we call with energy? EDS detectors have generally been calibrated by taking a measurement on a cobalt or copper peak and aligning that measurement with the energy for copper or cobalt. And then this gives a fair calibration of what other elements we detect, since we know the energies of those elements. And when we perform this kind of calibration, the results that we obtain nowadays with EDS are fairly accurate. What we have here are the results of, or the comparison of the known composition of some matrix matched samples from Rio Tinto versus mineralogic analysis. So these are samples that Rio Tinto use for calibration of their systems, and they know the composition of these samples extremely well to a very high precision. And so if you imagine the values would be represented along the x-axis. On the y-axis, we have the results from the normalized quantification using Mineralogic. The black line is the one-on-one fit. And as we see, there is some deviation in the analysis from the one-on-one fit. It's not perfect, but it's good enough if all we need to do is classify the mineralogy. If I want to be able to say, this is a bornite, this is a chalcopyrite, this is a pyrrhotite, then this is sufficient. However, if I need a higher precision in the analysis, if I need to know the elemental values to a high precision, then we can calibrate the ZEISS detectors with standards in a similar manner that we would do if we were using an electron microprobe and WDS detectors. In that case, we have a much tighter fit of the values that Mineralogic obtains compared to the known sample. In fact, it's very close to being a one-on-one match. And for major element composition, it is in an order of accuracy similar to that of the electron microprobe. But these analyses take milliseconds, units of milliseconds or less, compared to seconds or minutes on an electron microprobe. So having performed the analysis, we then immediately have some data available at the end of the run. The first table I'm going to describe is the bulk data table. It includes the mode of mineralogy, and this can be sorted by area or weight percent, average grain size. And in the columns, what we have from left to right is number, which is the number of instances of that phase in the sample. The area percent it represents in the sample, the weight percent, the average grain size, and the grain size standard deviation, or the average standard deviation, and the average composition of that phase. Now we provide an average grain size because this is tabulated, but the grain size for each of the 1,333 instances of monocyte serum are available in the database and can be interrogated. Since we measure the chemistry to a high level of precision, we can report a measured assay for the sample, and report an assay and the distribution. So what we can see in this table, for example, is that the assay for cerium, which is the second column, we have that 48% of the cerium, or the sample contains 48.04 weight percent cerium, 48.02 cerium is a monocyte cerium, which represents 99.96% of the cerium present. Usually in automated mineralogy, this data is approximated using an electron microprobe, where the sample that's been analyzed automatically is then transferred to an electron microprobe to obtain an average composition that is then attributed to the phases present. We provide a degree of liberation with user-defined percentage surface area to distinguish the percentage of logged, middling, and liberated target minerals. Associations, which may be reported as contact associations, as in the example below, but we also report lock-in associations. These are where phases occur in the same particle, but not in direct contact with each other. And we also report on particle classifications, what we call lithology. So far, we have described how we classify grains, phases within the analysis, but we have the ability to classify particles and types of particles. And these classifications exist in their own library, and during the analysis, the particles will be classified automatically. So we could create classifications such as a quartz sericite, that's porous, because we can use them, add the morphology to these classifications also, or sulfide, chalcopyrite sulfide grain. So these are particle descriptions, no longer just grain descriptions. These require knowledge of the mineralogy of that particle, the size of the granularity, and any morphological features that we want to add to that classification. So having analyzed the grains, which is the easier part in automated mineralogy, and then providing a general description of the particle itself, according to its mineralogy and the proportion of mineralogy present, we then now classify what we call the lithology, which is the description of a specific type of particle. And not only do we provide the modal mineralogy of that particle or the liberation of that particle, but we can also provide the chemical composition of that particle as an average, and then compare that to the material assay itself. So particle chemical composition, mineralogy, and morphology to characterize the particle. And this is where Mineralogic takes a step further and beyond what has been done in the past, what we have done up to now, indeed. We're no longer looking at the grain or a specific mineral. We're now looking at the type of particle that we're recovering in the process and how that affects our revenue. So the output for this, the mineralogy lithology, is similar to the bulk data output, but here what we have is the number of that type of particle that we describe, the area percent of the particle present, the weight percent, the average particle size, and then the modal mineralogy of that type of particle. So not just the phases that we're interested in, but any phase that's present in that particle and in what modality, as well as morphological features. In this case, we are measuring the porosity. So of interest in this table is you may note that chalcopyrite abundance in porous quartzite is highest, but much lower in the low porosity quartzite. This mineral appears dispersed across all gangue lithologies with no preferential occurrence in any one. However, overall, the sample contains mostly quartz sericite and sericite lithologies, quartzite lithology less abundant. Although some pyrite is dispersed through all lithologies, it most commonly occurs as large nuggety particles that are dominated in pyrite. This is the sort of information that you require when you're looking at the processing of the material in question. And we go one step beyond by providing the lithology chemistry. And here we'll provide the average composition of these particles, as well as an assay and distribution itself compared to the sample assay distribution. And of interest here, you may see that if we move to the average composition and the fourth column, and we travel down, we get to values of 27.63 weight percent copper for sulfide CCP, which would be a sulfide chalcopyrite, and 37.54 copper for sulfide enstatite. So this is approximately a 60-40 split of the copper content of the sample, if you like. So we're obviously very interested in recovering the sulfide enstatite in this case, but we can also see that that would then bring 13.75 weight percent arsenic into our concentrate. In fact, it's almost 90% of the arsenic in this sample is in the sulfide enstatite. So maybe we need to filter through our database and explore those particles to see what else we can do in the recovery process or the liberation process to ameliorate this situation. And this is very powerful information that is provided automatically at the end of the analysis. So that's a quick run through of how we classify the mineralogy and the particles themselves, and some of the outputs that are immediately available at the end of the analysis. They require no post-processing. So how do we perform the analysis itself? Well, we use a high resolution image starters, so we obtain the input image, and then we'll use image processing to find the areas of interest. In this case, we only want to analyze the particles. We don't want to be analyzing the black area, obviously, because that's a resin that contains the particles in this particular specimen. perform image analysis, and here we'll obtain 23 or up to 23 separate morphological measurements of the particles and the grains, possibly. And then we perform the EDS analysis and quantification of the EDS in order to classify the mineralogy. We have several data acquisition modes, again, trying to add flexibility. You don't always want to ask the same question of every sample, and this allows you to refine your question, but also save time. Our most extensive analysis is full mapping, where a figurative grid is overlaying the entire sample, and analyses are performed at the intersections, and of course the step size is determined by the user. But this then assigns mineralogy to each pixel. It provides the highest analytical resolution, pixel by pixel chemical analysis and classification, and it helps eliminate chemical zonations and transitions in your sample. It's not always necessary to obtain that level of resolution for the analysis. We may just be interested in modal mineralogy or the associations or general liberation of the sample. In that case, spot centroid analysis may be more suitable. In this case, spot is analyzed in the center of each particle or grain that has been segregated through image processing. And that analysis, that classification is then attributed to the entire particle. If we look at any of these particles in this image, the larger ones in particular, where we have at least two tones of gray, it's immediately evident that there's more than one phase in these particles. So attributing the entire composition of one spot to the whole would be erroneous. So through image processing, what we can do is segregate those gray levels and then analyze each one of these pink or blue or green areas once and attribute that composition to those phases then. So that we end up with particles that are, or grains within the particles that are not ignored simply because they're in the center of the particle. This is a fast and efficient method of analyzing. One composition assigned to each grain in the particle, and this is again possible because of the advanced image processing we can perform. It's much faster than mapping. If you imagine any one of these larger particles may have required 200 spots if we were mapping, and probably require fewer than a dozen spots to be analyzed in this method. Using the BSC brightness is another method of classification. So we can either use it in addition to the mineral library, or we can actually classify on its own using the gray level. It's very fast, as no EDS analysis is required. And the resolution is that of the BSC imaging. So this is, in some ways, our highest resolution analytical system. I have an example here. What we have is an image. It's a 9.3 microns high, and the vein cutting through it ranges from 128 to 25 nanometers in width. The EDS analysis of that vein would not provide us with any sort of classification. It's a chalcocite in pyrite. The volume of interaction of the beam would mean that 99.9% of what's analyzed, if not more, is pyrite, and the chalcocite, or the amount of copper in the chalcocite, would then just appear as an error, within the analysis itself. It'd be below detection limit, most likely. However, if we use the gray levels to classify it, then we can immediately classify that vein as being chalcocite and the main area as being pyrite. It's analysis and classification at image resolution. It's the fastest analysis mode per data provided, and we have improved the BSZ detector in order to be able to capture these images at 220 milliseconds per frame, and that's the classification speed. You can imagine that at this level of magnification, a 30 millimeter diameter sample might take in the order of 16,000 frames to image completely. So doing this as fast as possible is the only sensible way to proceed, since most of the time spent, the classification will be the imaging. It allows us to easily discriminate between hematite and magnetite by BSE gray level only. And because of the advances in the BSE detector, we don't need to stretch the BSE histogram. Both Mineralogic results at the speed of imaging in effect. And since we can assign composition to these phases, this method provides the same outputs as all of our other analytical methods. We also provide a method for line scan. If modal mineralogy is all that we need, then analyzing a line through the center of a large number of particles provides the same modal mineralogy as mapping the entire sample. This has been proven time and time again. But instead of spending 1 or 2 hours analyzing a sample, we can spend a couple of tens of minutes doing so. So again, it's just providing efficiency and a flexible way in which to obtain the data that we need. The feature scan, it's the more traditional method to be used with EDS, where the beam is rastered over a particle, or in our case, we can segregate the grains out using the image processing to be per grain. And you, in this way, obtain an average composition of that particle or grain. And our latest acquisition method is what we call in fast scan, which is a faster way to obtain a quick scan of a grain. Instead of rastering through the entire grain or particle, several points can be analyzed on each grain, and the larger grains are analyzed with more points than the smaller grains. We have rules in the system that determine the surface area of the grain and calculate how many points it should analyze on it. So the very small grains might be analyzed once, things in the order of a micron might receive 1 spot, but I think in the order of 400 or 500 microns in size, when cross-section, might be analyzed a couple of tens of times, just to provide a better dispersion of the analysis. Then we have some latest developments in Mineralogic. Mineralogic is continuously evolving. We aim to have a release every 6 months or so, and we continuously add in features, calculations, outputs, and easier ways of operating. Of late, we've added stitching of the mineral maps and mineral data particles, and this happens during the analysis live. So at the end of the analysis, any particle that crosses over fields of view, and it doesn't matter how many fields of view it crosses, it's reconstituted into a single individual particle, and all the morphological, chemical, and classification parameters are calculated on that recombined particle, not on the fractions of the particle. This allows larger particles to be analyzed with high resolution and obviously improves data quality because we're not looking at fractions of a particle in our statistics, we're looking at actual particles themselves. I mentioned assigned compositions briefly earlier. I'll go into a bit more detail now. So it's possible to import and assign elemental composition data of a mineral from external sources or manually. So in this example here, we have pyrite, and we have a min-max, which might be the parameters within which the iron concentration has to exist, and the sulfur concentration and zinc concentrations have to exist in order for it to be, this analysis to be classified as a pyrite. But we can actually assign a composition to the iron, so that once an analysis has been classified as a pyrite, in the calculations and in the outputs, the iron will have 42 weight % iron. It would not be a 26 weight % iron, for example. Now, we don't discard the analysis. We provide the data in 2 ways. So there'll be a set of data that is for the measured analysis and a set of data for the assigned composition analysis. This allows us, for example, to add elements such as hydrogen or lithium, which we cannot measure during the analysis. to the classifications themselves to provide a better picture. So we could specify that our goethite contains 1% hydrogen if this were significant to our method of analysis. Or if we analyze this spodumene, we could add lithium to it in order to have that value come through. And the measured values are adjusted adjusted to take account of these assigned compositions. So in the lithium bearing phase, where the assigned column has a value for lithium, the measured values are then adjusted so that we don't end up with 104% total for our analysis, but it's adjusted to 100%. We can now reconcile assays automatically. So the measured assays compared to an imported assay for that sample. And after the calculation or the comparison, the analysis node will either be illuminated in red or in green, depending on whether the difference between the imported or control assay and the measured assay are within the allowed parameters or outside of those parameters. And within the assay data table itself, those assays will be highlighted in lighter red so that we can immediately see that as far as sulfur and copper are concerned, we are within the allowed parameters, but titanium differs markedly from the control assay, which may have been performed with a higher resolution technique. And we can now export all the data generated by Mineralogic to Excel automatically at the press of a button for further analysis and plotting. And within the batch exporter, you can use a simple wizard to create tables. And these are then stored. You don't have to create them every time. So if you have a graph or a set of data that you export regularly, you create this using the wizard, and then it's essentially at the end of the analysis requesting that output to be exported as an Excel spreadsheet so that the graphs can be produced. And data can now also be merged within the Explorer software, not just the reporter software, which is simpler for customers to create reports in this way. Lastly, we have moved stock criteria out of the recipe tab and created its own tab. This is because in the near future, excuse me, there are going to be software updates and developments which are going to allow us to assign these to different samples, and it's going to be removed out of the recipe itself, or the analytical recipe itself. We believe that this will allow or provide a higher level of flexibility to the analysis. So in summary, Mineralogy represents a next generation automated mineral analysis, incorporates cutting-edge image processing, image analysis, and quantified EDS, permits rapid chemical and morphochemical analysis with mine-relevant data outputs available at the end of the run. It's platform independent, which provides flexibility. You can buy the right microscope for the task at any stage. And quantification of the spectra means that mineral libraries and analysis setups can be performed at a central location and deployed to all systems with ease. Since we're not dependent on a specific amplifier or specific detector, and we're not looking at the spectra itself, but we're actually quantifying that spectra, the quantification method is the same for all the systems. So mineral libraries can be created centrally with ease, since we're using the stoichiometry of the mineral, and emailed and rapidly imported into any mineralogic system in the field. Thank you very much for your attention.